Well, as said, my name is Lucia Morales-Rivas from the National Center for Metallurgical Research in Spain, and I was also affiliated in the past to the Technische Universität Kaiserslautern in Germany. Now it's called Rheinland-Pfälzische Technische Universität, RWTU. Well, let me start, please, with an introduction on the microstructure about which I will talk. This is a nanostructure by night, and these microstructures are based on steel that are they have a quite lean chemical composition. Among other elements, we have high carbon contents and high silicon contents, and these microstructures are produced by a heat treatment consisting of a first stage of austenitization plus following isothermal holding to enable the magnetic transformation. The high silicon contents lead to the absence of coarse and massive carbides, and this is because during the transformation there is a carbon partitioning from the magnetic ferrite into the surrounding austenite. Therefore, this phase, the austenite, gets enriched in carbon and is metastable at room temperature, at retained austenite. And the high carbon contents enable the transformation at a very low, not very low, but between 200 and 350 degrees temperature, and so leading to a refinement of the microstructure. If we go to the nanoscale, we can observe this DM, and we see that there are even films of austenite with a thickness of some tens of nanometers between plates, also very thin, of magnetic ferrite. So in general, what we have is basically these two phases: magnetic ferrite, which is VCT with a small tetragonality, and austenite, that is the crystal structure is FCC. If we go to other scales, we see here an ACM micrograph. We see that the austenite is in a very heterogeneous morphology and shapes and sizes, ranging from these nanofilms that I showed before to coarser films and also to coarser blocks of austenite that you can see. Sorry, I don't know. But as we can see here, in the submicron scale and also even the micron scale. Then I show here the crystallography of these microstructures with these two EBSD maps. Here we see the FCC, the austenite, and here we see the iron BCC, what we index as iron BCC, which is magnetic ferrite. So the orientation of austenite obviously remains with the orientation of the prior austenite, and the magnetic ferrite, we can observe that there are like grains of this phase, magnetic ferrite, but in fact we know that inside these grains we have both phases, FCC and BCC, what is in this as BCC. So magnetic ferrite, the thing is, as I mentioned before, the austenite can be so fine that we don't have enough resolution to observe them by EBSD. And more in detail, we need to consider that this transformation, magnetic transformation, has a displacive nature, and it leads to a fixed orientation relationship between austenite and magnetic ferrite, between Kuryumov-Sachs and Nishiyama-Wasserman. So what it leads to a very hierarchical structure, and we will have boundaries of the prior austenite grains. Within them, we find packets of bainite where the different variants that are present, variants of magnetic ferrite, share a plane of the family 110 that is common, that they are coplanar. And if we go, and it's also coplanar to one plane 111 of the family 111 of the austenite. If we go to a lower scale, we find blocks like this of bainite, where we find a single magnetic variant or a low misoriented variant. So what I want you to remember from this small introduction is that for nanostructure bainite, we have an absence of coarse carbides, There is metastable retained austenite, phase FCC, that can transform into martensite under mechanical loading. We have microstructural features down to the nanoscale, and we have a highly hierarchical crystallographic structure. And now I will present results on fatigue. The idea is to determine what is affecting the notch sensitivity in this material, and we will compare them to the response of other high-strength steels, more conventional, like tempered martensite, 100 chromium 6. For that purpose, we have used different fatigue specimens with a blunt notch with a different stress concentration factor, with the idea to isolate, to separate the effect of the geometry of the specimen and the effect of the material itself. So doing so, we can apply this equation that is based on Neuber in order to determine the KF, that is this ratio, the threshold of the stress, nominal stress range over the theoretical fatigue limit of the smooth specimen. If we plot this equation for the case of a tempered martensite, we have a curve like this with two asymptotic behaviors. At this side, the curve tends to this threshold, which is the non-propagation threshold for long cracks. And at this limit for this stress ratio, 0.1, the limit is tends to the inverse of KT, of the stress concentration factor. So in between, we have this region here where the crack initiation, either crack initiation or crack propagation is not enabled. And it means that when we have introduced a notch, there is a volume effect, there is a side effect, and therefore the volume of material that is subjected to critical loading is important. Now we see here the experimental results on KF for nanovinyl, and we see that in this case the values exceed those of the tempered martensite. So meaning that we are still in a safe region, that it would not be the case for the tempered martensite. And this is something that is not explained by the ratio of the yield strength over the UTS, as we can see here, that because it's even higher for the case of the tempered martensite. So in order to try to understand if there are some critical microstructural features that can explain this, we have performed in the past some crystallographic analysis. In this case, this is a different condition, but also for this kind of specimens, fatigue specimens that I showed before. And we examined a failed specimen, okay, at the cross section with respect to the fracture surface. These are the results where we see here the map, and we wanted to understand how is this crack path, and whether we can explain this crack path. So here we plotted the traces of the planes for the sleep systems that are activated theoretically according to the highest Smith factor. And what is interesting, just considering binary ferrite, is that this theoretical crack path mimics quite well the actual crack path of our specimen. So it indicates in an analogous way that we would be in a stage 1 where single primary sleep rules. So something analogous to the situation where we would have a single phase, even though in this case we have also austenite in between. Moreover, these are some new results where we can see that here, if we consider the longest straight section of the crack, we see that it's almost parallel to to this trace, which corresponds to the plane of the family 110 of these two blocks of magnetic ferrite that are coplanar to one plane of the family 111 of the prior austenite. So it indicates that in that case, there is less restriction for sleep, or dislocation sleep, to be transmitted across the interfaces between magnetic ferrite and austenite that we cannot see at this with this EVSD map. And we have also performed a more recent work in order to track the crack path at the surface, also in nanostructure bainite. And in this case, what we have is a flat specimen where we manufacture before and with FIB, with focused ion beam, an artifact like this in order to induce the crack initiation close to the tip of to the root of this artifact. And it is interesting that in all cases we see a common pattern. Here I show just some example, but there is a common pattern where we observe initially there are sections having kind of a V morphology of the crack before the crack starts growing in a direction that is globally normal to the applied loading direction. So analyzing this, and here I show also just one example where we see these micrographs based on the backscatter electron on the surface, polysurface surface. So this is just the phase and crystal orientation, what we can observe here. Right? And in this case, we see the EVSD map. It's interesting because we have like two micro cracks, which are these straight sections that are confined to packets of magnetic ferrite, and through this packet, the crack globally does not change this the path, although it's crossing interfaces of austenite and magnetic ferrite. And also doing another trace analysis, we can see that there is a parallelism between the microcracks and this trace, which corresponds to the plane of one of the planes of the family 110 for both the magnetic variants that we observe here. That is also coplanar to one plane 111 of the prior austenite, as we can see here, which is in good agreement with the previous results that I show on the bulk specimen. So this is something that can suggest that there is a restriction to the activation of sleep preceding initiation of critical cracks in nanostructural bainite, and that magnetic packets optimally oriented can act as a scatter critical microstructural features for potential crack initiation. So these are the conclusions, and I think well, I will finish here. Thank you. Thanks also to the funding institutions.